For centuries, humanity has gazed at the stars, wondering about our place in the vast cosmic tapestry. Our home, the Milky Way galaxy, is an immense island of stars, gas, and dust, spanning perhaps 100,000 light-years across. Yet, for much of history, our understanding of its true structure and the intricate dance of its stars was profoundly limited. We knew we lived within it, but we lacked a comprehensive map, a precise understanding of its depth and motion. Imagine trying to navigate a bustling city without a map, knowing only the immediate streets around you. That was our galactic predicament. In 2013, the European Space Agency, or ESA, launched a groundbreaking mission designed to fundamentally change this. It's called Gaia, named after the ancient Greek goddess personifying Earth. Gaia is not a telescope in the traditional sense, peering at distant galaxies. Instead, it's a dedicated astrometry mission, meaning its primary goal is to precisely measure the positions, distances, and motions of stars within our own Milky Way. Think of it as a celestial surveyor, silently charting the heavens with unprecedented accuracy. Its task, to create the most accurate and complete 3D map of our galaxy ever conceived. Mapping the Milky Way is an astonishingly complex undertaking. Our galaxy contains hundreds of billions of stars, each moving in its own intricate path. From Earth, these stars appear as fixed points of light, but they are constantly shifting, albeit slowly, across vast cosmic distances. To understand our galaxy's evolution, its past collisions, and its future, we need to know not just where stars are, but where they are going, and how far away they truly are. This requires measuring minute shifts in their apparent positions from our moving vantage point in space, a challenge that demanded a new level of precision. At the heart of Gaia's mission is a science called astrometry. Astrometry is the branch of astronomy that deals with the precise measurement of the positions and movements of stars and other celestial bodies. For centuries, astronomers have used astrometry to create star catalogs, but the precision was always limited by Earth's turbulent atmosphere and the narrow baselines available to ground-based telescopes. Gaia takes this art to space, far above atmospheric interference, using two powerful telescopes that scan the entire sky, collecting light from stars as they drift into its field of view. One of Gaia's most crucial measurements is parallax. You can demonstrate parallax yourself. Hold your thumb out at arm's length and alternate closing one eye, then the other. Your thumb appears to shift against the background. This apparent shift is parallax. Astronomically, as Earth orbits the Sun, our perspective on nearby stars changes over 6 months. A star appears to shift slightly against the much more distant background stars. By measuring this tiny angular shift, Gaia can calculate a star's distance. The smaller the shift, the farther away the star. This geometric method is the most reliable way to determine stellar distances. Beyond distance, Gaia also measures what's called proper motion. Imagine observing a sailboat far out at sea. Even if it's moving, it might appear stationary from a distance. But over time, if you keep watching, you'll see its position change relative to the distant horizon. Proper motion is the apparent angular movement of a star across the sky, caused by its actual physical motion through space. It's the sideways component of a star's velocity. Gaia observes each star multiple times over its mission lifetime, allowing it to detect these incredibly subtle shifts, revealing how stars are actually drifting across the galactic stage. To complete the 3D picture of a star's motion, we need one more piece of information: radial velocity. While parallax tells us distance and proper motion tells us sideways movement, radial velocity tells us if a star is moving towards or away from us. This is measured using the Doppler effect. Just like the pitch of a siren changes as an ambulance approaches or recedes, the light from a star changes wavelength. If a star is moving towards us, its light shifts to bluer wavelengths, blue shift. If it's moving away, it shifts to redder wavelengths, redshift. Gaia's instruments meticulously measure these shifts, providing the full velocity vector of a star. To achieve its extraordinary precision, Gaia orbits not Earth, but a special location in space called the L2 Lagrangian point. L2 is about 1.5 million kilometers, or nearly a million miles, away from Earth, in the opposite direction from the Sun. At L2, the gravitational forces of the Sun and Earth balance, allowing Gaia to remain relatively stationary with respect to both, using minimal fuel. This stable, sun-shielded environment provides Gaia with an unobstructed, consistent view of the entire sky, free from Earth's glare and atmospheric distortions, making it the perfect platform for its intricate measurements. Gaia is equipped with 2 optical telescopes, each providing light to 3 main scientific instruments. The astrometric instrument precisely measures star positions. The photometric instrument determines the brightness and color of stars, which tells us about their temperature, size, and composition. Finally, the radial velocity spectrometer analyzes the tiny shifts in starlight to measure their motion towards or away from us. These instruments work in unison, meticulously collecting data across the entire celestial sphere. Imagine a digital camera with 1 billion pixels, taking pictures of the entire sky, every few months, for years on end. The sheer volume of data collected by Gaia is staggering. Its instruments sweep across the sky continuously, detecting and processing about 100,000 stars per minute. Over its mission lifetime, Gaia has observed billions of stars, repeatedly. This isn't just a snapshot, it's a cosmic movie, capturing the movements of our galaxy over time. The raw data stream is immense, requiring sophisticated processing on Earth to transform these observations into precise measurements of position, motion, and stellar properties. It's an unprecedented effort in astronomical data collection and analysis. What truly sets Gaia apart is its extraordinary precision. Its astrometric measurements are so accurate that if you were to stand on Earth and look at a human hair on the Moon, Gaia could tell you its width. For a star at the distance of 1,000 light-years, Gaia can determine its position to within the width of a human hair. This level of detail allows astronomers to discern minute shifts in stellar positions and velocities that were previously undetectable. It's like upgrading from a blurry, grainy photograph to a crystal-clear, high-definition image, revealing details we never knew existed. The culmination of Gaia's work is an incredibly detailed 3D map of the Milky Way. Previous star maps were largely two-dimensional, or based on statistical assumptions. Gaia provides direct measurements for nearly 2 billion stars, pinpointing their exact locations in 3-dimensional space and charting their trajectories. This isn't just a static map, it's a dynamic model, showing us not only where stars are, but also how the entire galaxy is rotating, how stars move within its spiral arms, and how different populations of stars interact. It's like constructing a complete anatomical model of a living, breathing organism. With Gaia's data, astronomers can essentially turn back time, reconstructing the Milky Way's history. By observing the motions of stars, we can see evidence of past galactic mergers and collisions. For example, Gaia has revealed stellar streams, remnants of smaller galaxies that our Milky Way has swallowed over billions of years, whose stars are still moving together in coherent paths. These discoveries provide crucial insights into how our galaxy formed and evolved, growing through gravitational interactions and cannibalizing its smaller neighbors. It's like finding archaeological evidence of ancient cosmic battles. While Gaia's primary focus is stars, its incredible precision has also enabled discoveries beyond. By detecting tiny, periodic wobbles in a star's proper motion, Gaia can infer the gravitational tug of unseen companions, such as exoplanets, planets orbiting other stars, or even brown dwarfs. Brown dwarfs are often called failed stars because they are too massive to be planets but not massive enough to ignite nuclear fusion like true stars. Gaia's data is helping to characterize these elusive objects, adding to our understanding of planetary systems and the diverse populations of objects in our galaxy. Gaia's map also offers new ways to probe the mysterious dark matter. We can't see dark matter, but we know it exists because of its gravitational effects on visible matter. By precisely mapping the motions of billions of stars, Gaia allows astronomers to trace the gravitational field of the Milky Way with unprecedented accuracy. Any discrepancies between the observed motions of stars and the gravitational field predicted by visible matter alone point to the presence and distribution of dark matter. Gaia is helping to refine our models of dark matter's halo around our galaxy, a crucial step in understanding this elusive cosmic component. Gaia's mission officially ended its data collection phase in 2024, but its legacy is far from over. The vast trove of data it collected will continue to be analyzed by astronomers for decades to come, leading to new discoveries and refining our understanding of the cosmos. New data releases will continue to be published, each one a gift to the scientific community. Gaia has not only provided a snapshot of our galaxy but has given us a dynamic, evolving picture, transforming galactic astronomy into a field where we can precisely track and model the intricate movements of stars. It's a testament to human ingenuity and our endless quest to understand the universe. From its lonely perch at L2, the Gaia satellite has indeed been a silent cartographer. Without a single human on board, it has meticulously mapped our galactic home, transforming our understanding of its scale, structure, and dynamic history. Before Gaia, our Milky Way was like a mysterious, veiled landscape. Now, we have a detailed, high-resolution map, revealing its mountains, rivers, and changing seasons of stellar life. Its impact resonates across all branches of astrophysics, from stellar evolution to cosmology, proving that even in the vast silence of space, the most profound stories can be told through the quiet, persistent measurement of light. Gaia truly is a beacon of scientific exploration.